So now we will talk about some methods that are known to be quite good as ensemble methods, bagging, random subspaces, and random forest. So bagging and random subspaces are kind of related. They are similar in many ways. The idea of bagging, for instance, is to build up an ensemble of classifiers where we will train every classifier on a different subset of data. So we will have the first, I would say, the training set. And what we do is to pick up a new training set for every classifier we are training, and we are making a drawing with replacement. That means that we can pick up the same data instances many times, but usually we will get with the same size of training set. So if we have a training set, an original training set of n samples, we will pick up n samples for each xj, but we can get 2, 3, 4 times the same sample, a given sample, and no instances of another sample. So this kind of sampling is good when we are dealing with basic classifiers that are unstable. So by unstable training algorithms, we mean that from just varying a little the training set may lead to quite different classifiers in the end. The behavior may be modified a lot only by changing this training set, even if we just pick up from the same pool of data. And I would say in a position, stable models are something like k-nearest neighbors, parametric classification. So these are stable models, so these will not behave pretty well. It will not be a good fit to use that with bagging, but unstable approaches, like I would say multi-layer perceptron or add condensation, which is used for k-nearest neighbors classification, are much more sensitive to the training set, and this can be used for that. This can be useful, in fact, for that. So in general, we say that unstable algorithms have a large variance. So from one training to another, it may lead to very different results. So that's the point of being unstable, is to change a lot in terms of the decision based on the same conditions. So we have a large variance that is observed, that is coming from some randomness and some ways the model is learning. And I would say then the sibling of bagging is random subspaces. So the idea here is that not to sample the training data set with replacement from the original training set, is in fact to sample a subset of features. So let's not use all the inputs, all the features input. Let's use some of them, maybe half of them, for example, pick them randomly and train many models with different subsets of features. This is likely to induce a lot of variations, especially for data set based on, I would say, high-level measurements, not images. You know, if you just sample half of the pixels, it should be okay. But if you sample half of the numerical values describing some specific stuff with different measurements over different units, for example, this may hurt, this may change quite significantly the model that is trained from that. In fact, one of the models that we are often using is, I would say, the common model used with bagging, boosting random subspaces, at least when it was proposed, is decision trees. You know, this idea of decision trees is to build up some kind of hierarchical separation of the input space. We will split the input space at fixed thresholds over given variables, but hierarchically, you know, going through a kind of binary tree that is making that processing. So every node in that tree, in that binary tree, or we can be also NRE in the sense that we can make decisions over different classes if it is relevant. So we are testing each node for a value with discrete outcomes. So if it's the binary outcomes, it will be binary tree. If it's like not a discrete one, but with many cases, we will get that many different branches from that node. And the point is that we are performing a finer and finer division. You know, going at the root of the decision tree, we just split in two, for example, or in some cases, the complete data set, but then going in like the left branch is only taking the part that is assigned to the left branch. It can be, I would say, in terms of binary trees, equivalent to half of the samples approximatively, that is going that way and the other half is going the other way. It can be quite unbalanced. It depends on what we are doing. And you notice half is still cut in two and still cut in two and still cut in two until we reach the leaves, where the leaves may make decision based on really just a few dozen samples. So the point is that we usually construct the trees in a top-down approach. We start from the root and we try to kind of split the dataset in a current way according to the labels. And we do that repeatedly. So we can use, for example, entropy as a metric to measure that, to define how we make the splits. But in the end, we possibly get quite big decision trees that may overfit a lot because they are over specializing. And like I said, possibly the decision in trees are based on very few samples, which is not good. So we can then do some pruning. So we will just cut back several elements in the tree to shrink it in something smaller. But this something smaller should generalize better because we will have decision based on more samples. And as such, decision trees has been proposed a long time ago, 80s, 90s. It was used quite at that time. It is not that much popular right now in machine learning. They are more with, I would say, numerical models, neural network models. But it was something that was big in the 90s. And one of useful elements from that is that it's kind of useful to extract extemporatable decision rules. So the decision rules can be, I would say, not easily interpretable, but interpretable by humans if we are looking at every nodes, what are the decisions, and we can build up something like that. And in fact, in some fields, decision making may be based on decision trees, manually designed decision trees this time. So an example of decision trees here, we have this root here that is stating, well, so this is the root. So we have a threshold on the start. So let's say start is bigger than 8.5, yes or no. If yes, then its start is in fact bigger than 14. If yes, it's really a 0 with high confidence. So then we just split according to age. So the two first were about the start. The two last are about age. So we know that these two age decisions are basically for a start between 8.5 and 14, because if it was less than 8.5, we will go that way. If it was more than 14, it will be that way. In between is in between 8.5 and 14 in terms of start. And then we are splitting according to age. So if the age is less than 4.6, so it's this thing, 0. If the age is more than 9.2, is that thing. In between is that thing. So we can see how it goes here in terms of the splitting. So this is in 3D. So we have the start and the age and the probability present. So we see this as that kind of space. So, you know, I would say everything in there is for that branch. That part is for that branch. We have the top one, which is basically this. And we have in between, or I would say that one is that thing, and that one is that thing. So basically you see the different floors, the different, I would say, levels in the 3D plot that is corresponding to different decisions according to the leaves of the decision tree. And we can see in 2D the split according to start and age. Then we can see that it is, I would say, the gray shade correspond to the value that we have corresponding to that. And we see that in fact the absent and present are the real labels of each sample. So these were more based on some kind of confidence or some kind of average over the labels, while the real labels are presented with the samples on the right. So a problem with decision trees for classification is that these models are known to be low bias because they are able, in fact, to fit super well a training set. So, you know, with enough levels, if we go with deep, I would say, decision trees, these decision trees will be able to learn everything because they will just have enough leaves to model everything and have, I would say, 100% accuracy on the training set. But on the test set, that's something quite different. There's a big overfit possible with this decision tree. So basically, these are classifiers with really low bias because they can fit anything. But there are some models with high variance because from one set of samples to another, the trees can be much different based on some small changes in the training set. So even if pruning is used, we are in a case of high risk of overfitting, and this is known to overfit. So a solution is to make an ensemble of trees. So the idea is to say, okay, the bias is low, that's good. If we are averaging over low bias models, we will keep the bias low for our ensemble. But if we are facing high variance models, averaging over these high variance models will lead us to an ensemble that should have a reduced overall variance. But the trick is to induce some kind of diversity in the trees. We should not get the same tree repeated all the time. If we have L models, we don't have L times the same decision tree. The trees should be different. So the point is to generate some kind of randomized trees that are different from one case to another. And for random forest, we do this by doing some bagging and random subspaces. So the idea is that we are sampling a subset of the training set and sampling a subset of the features. And we are learning on that. So the learning is done. So in fact, at every node, we are doing this. So from one node to another, we are sampling the subsets, the features available differently. We are sampling the training set for computing things in our tree differently. So basically, it's kind of building up a random tree, set of random trees based on the data, but with subsampling. And we see that somehow we get, well, instead of having one tree, we get a set of trees, which is a forest. And given the randomness introduced in the creation of these different trees, we get what we call a random forest, where the decision basically is based on averaging every single tree decisions. And we could even state that the variance measured on that is a good indicator of the overall confidence. If there are some ambiguity, if some classifiers, decision trees are giving one decision versus another one, that means that we have some level of uncertainty. We are not sure about that decision. And this is, I would say, a good way to empirically measure it.